In this lecture, we're going to introduce the entropy balance for closed systems. As a closed system undergoes an internally reversible process, its entropy can increase, decrease, or remain constant. Pretty much what I'm saying is that ds is related to our heat transfer for our internally reversible process. This equation tells us that when a closed system is undergoing an internally reversible process, and receives energy by heat transfer, the system experiences an increase in entropy. If energy is removed by heat transfer, the entropy of the system decreases. We can conclude from this that entropy transfer accompanies heat transfer, and that the direction of entropy transfer is the same as the direction of heat transfer. In an adiabatic internally reversible process, entropy remains constant, and a constant entropy process is called isentropic. This is a point that's going to come up more than once. If we rearrange our earlier equations, we have that our heat transfer is equal to TdS. And if we integrate, we get that our heat transfer for our internally reversible process is equal to the integral from 1 to 2 of T times ds. It follows that the energy transfer by heat to a closed system during an internally reversible process is represented by the area on our TS diagrams. To do a quick example, we have water initially at a saturated liquid at 150 degrees Celsius. It's contained in a piston cylinder assembly. The water undergoes a process to saturated vapor, during which the piston moves freely in the cylinder, which means there's no friction. If the change of state is brought about by heating, the water undergoes an internally reversible process at constant pressure and temperature. We want to determine the work and heat transfer per unit mass. Our work is still the integral of PdV. Since it's constant pressure, it's our pressure times our change in specific volume. So we need our states. So state 1 is saturated liquid at 150 degrees Celsius. We know that VF is 1.0905 times 10 to the minus 3. And state 2 is saturated vapor, still at 150 degrees Celsius. So we know that Vg is 0.3928 meters cubed per kilogram. Our work is equal to our pressure, which is 4.758 bar. That's the saturation pressure at 150 degrees Celsius, times our change in volume. Our work per unit mass is 186.38 kilojoules per kilogram. To find the heat transfer, we're going to use entropy, and since the process is internally reversible, we know that Q is equal to the integral of TdS. Since temperature is constant, we're going to get our heat transfer per unit mass is T times our change in entropy. Or this is SG, and this is SF. So our Q per unit mass is 423.15 Kelvin times 68379 minus 1.8418, which is 2,000 114.1 kilojoules per kilogram. Well, why do we care about all this? We care about this because we're going to expand this concept to include the idea of an entropy balance for closed systems. Pretty much the entropy balance is the change in the amount of entropy contained within the system during some time interval is equal to the net amount of entropy transferred in plus the amount of entropy produced within the system. So our change in entropy is equal to our entropy transferred in by heat transfer plus our entropy production. We can also write this on a differential basis. In accordance with the interpretation of sigma cycle from the Clausius inequality, if sigma equals 0, there's no reversibilities. If sigma is greater than 0, there's irreversibilities. And a sigma less than 0 is impossible. So the first term on the right-hand side is entropy transfer accompanying heat transfer. It has the same sign convention as heat transfer. A positive value means entropy is transferred into the system. A negative value means entropy is transferred out. When there is no heat transfer, there is no entropy transfer. Sigma having a value of 0 means there's no internal irreversibilities, and it's positive when there's irreversibilities present. This leads to the interpretation that sigma accounts for entropy produced or generated within the system. Again, I want to note that entropy production is not a property. We're going to look at an example where we have water initially at saturated liquid at 150 degrees Celsius. It's contained in a piston cylinder assembly. The water undergoes a process to the corresponding saturated vapor state, during which the piston moves freely in the cylinder. There's no heat transfer with the surroundings. If the change in state is brought about by the action of a paddle wheel, we want to determine the net work and the amount of entropy produced per unit mass. So if I start with my energy balance, I have my change in internal energy plus my change in kinetic plus my change in potential is equal to my heat transfer minus my work. Well, there's no kinetic, there's no potential, and there's no heat transfer. So my work per unit mass is going to be equal to my change in internal energy. We'd get our U's from table A2 since they are saturated liquid and saturated vapor. So it's minus 2559.5 minus 631.68, which is minus 1927.82 kilojoules per kilogram. Nothing in this part is really new, but now we're looking for the entropy produced. So delta S is equal to our integral plus sigma. So sigma per unit mass, again, this is going to go to 0, is equal to our change in entropy, which is 6.8379. Which means our entropy produced is 4.9961 kilojoules per kilogram Kelvin. To look at another example, we have 5 kilograms of CO2 undergoing a process in a well-insulated piston cylinder assembly from 2 bar and 280 Kelvin to 20 bar and 520 Kelvin. If the carbon dioxide behaves as an ideal gas, determine the amount of entropy produced, assuming a constant specific heat and variable specific heat. So we're going to do the problem 2 ways. First one is assuming constant Cp. Well, again, delta S is the integral from 1 to 2 of dq over t plus sigma. There's no heat transfer, so sigma is equal to our change in entropy, where our change in specific entropy is Cp times the natural log of T2 over T1 minus R ln P2 over P1, which is 0.939 times the natural log of 520 over 280 minus 8.314. So our change in specific entropy is 0.14629. So sigma is our 5 kilograms times 0.4629, which is 0.73145 kilojoules per Kelvin. If we were to do it with variable specific heats, that means we're going to go to the tables. Delta S is S naught 2 minus S naught 1 over molecular weight minus R times the natural log, which is equal to 0.73145. In this case, sigma is equal to 0.68975 kilojoules per Kelvin. The last thing that I want to go over in this lecture is just stating the fact that we can also have it be rate-based, so we know that our change in entropy is equal to our heat transfer over our temperature, which is occurring plus sigma. If this was supposed to be on a rate basis, we'd have ds dt is equal to sum of whatever heat transfer is occurring at whatever boundaries plus our rate of entropy production. That's it for this lecture. In our next lecture, we're actually going to go over the directionality of processes and the entropy balance for open systems.